Greetings, everyone. Thank you for joining us for resistance report and ship development using Maxif 2026. This is a group project for MMT4183 Advanced Naval Architecture with lecturer Dr. Syed Zainal Abidin Syed Ahmad. This is Group 3 presentation. First up, introduction. In the resistances, a scaled ship model is towed in a towing tank while the total resistance force is measured at various speeds. Turbulence stimulators are fitted at the bow to ensure a turbulent boundary layer, and the model is allowed to heave and pitch freely. The ITTC 1978 performance prediction method applies Froude's similarity law to separate total resistance into viscous and wave-making components. A form factor, 1 plus k, is used to account for the effects of hull shape on the viscous resistance, enabling accurate extrapolation of model test results to predict the resistance and power requirements of the full-scale vessel. Next up is the derivation of form factor 1 plus k. So Prohaska's method was used to determine the hull form factor 1 plus k from the model test data at low Froude numbers where Fn is less than 0.2. A graph of CTM divided by CFM against Fn to the power of 4 divided by CFM is plotted and a linear trend line was fitted. The y-intercept of the trend line represents the form factor 1 plus k, which accounts for the additional viscous resistance caused by the three-dimensional hull shape. This form factor is then used in the ITTC 1978 performance prediction method to extrapolate model resistance results to full-scale ship resistance. Next up, what is ITTC 1978 performance prediction method? So the ITTC 1978 performance prediction method is a standardized procedure developed by the International Towing Tank Conference (ITTC) to predict the resistance and power requirements of a full-scale ship from model test results. The process is simple. In a towing tank, only a scale model can be tested, but ships are much larger and operate at much higher Reynolds number. Because frictional resistance does not scale directly between model and ship, the ITTC 1978 method provides a systematic way to separate the measured model resistance into its component and then extrapolate those components to full scale. The method assumes that the total resistance coefficients can be expressed as CTS equals 1 plus K multiplied by CFS plus CRS plus CA plus CAA, where CFS is the frictional resistance coefficient calculated using the ITTC 1957 friction line. The 1 plus K is the form factor obtained using the Prohaska's method. The CRS is the residuary resistance coefficient, mainly from wave-making resistance. The CA is the correlation allowance or roughness allowance, and the CAA is the air resistance, which in this test is ignored. In simpler terms, the ITTC 1978 method is essentially a model-to-ship conversion procedure. It takes the resistance measured on a small-scale model, corrects it for scale effects, the hull form effects, and the surface roughness, and predicts the resistance and power that the actual ship will require in service. It is one of the most widely used methods in naval architecture for ship powering prediction and is the basis of many calculations performed in software such as Maxif, Navcard, and towing tank analysis reports.
Next is objective. First, To carry out resistance prediction using model test for a 147.80 meters vessel in calm water condition. Second, to predict total resistance of ship using ITTC 1978 performance prediction method for given vessel particulars as shown in figure 1. Third, to present the result of the total resistance and the effective power for the vessel including the form factor prediction using Prohaska plot. Fourth, to compare the resistance and powering result from extrapolation, model test and prediction method, NAVCAD or MedSurf. The resistance test is divided into two parts, namely model making procedure and experimental procedure. The apparatus used in this study include MS Excel program for manual calculation, a towing tank and a 147.8 meter vessel scale model. Other equipment involved are the towing carriage, wave generator, wave absorber, trimming dock, buffer stop and rail. Next, looking at the model scale, Table 2 presents the main particulars of both the ship and the model based on a scale ratio of 50 to 1. The actual ship has a length overall of 147.8 meters, a beam of 21.8 meters, and a design draft of 8.7 meters, which translates to a model length of 2.956 meters, a beam of 0.436 meters, and a draft of 0.174 meters. Furthermore, the massive ship displacement of 21,635 tons scales down to a model weight of 168.86 kg, while the weighted surface area is reduced from 4,625 square meters to 1.85 square meters, ensuring strict geometric similarity for our testing. Next, for the model making procedure, a 1 to 50 scale model of the 147.8 meter vessel was constructed using gelatin wood and hand finished to achieve the required surface quality. The model was then painted yellow, while the fabrication tolerance was strictly maintained within plus minus 1.0 millimeters to ensure dimensional accuracy throughout the construction process. Next, for the step-by-step experimental procedure, first, a series of calm water resistance tests was conducted as the test program. Second, the model was tested at the following conditions with a speed range of 8.0 to 70.0 knots at 1.0 knot increment at a displacement of 22,271 tons. Third, the model test speed in the towing tank were determined based on corrected speed values ranging from 0.580 to 1.2367 meters per second, with float numbers from 0.1081 to 0.2297, ship speeds from 8 to 70 knots, and model total resistance from 1.752 to 3.123 newtons. A representative model test conducted at a speed of 0.873 meters per second is demonstrated in figure 3 to show the calm water wave profile. Fourth, the test was conducted considering the water properties of the towing tank and seawater conditions, specifically a towing tank temperature of 24 degrees Celsius and seawater temperature of 15 degrees Celsius. Fifth, the total resistance for the model for various speeds was obtained with reference to the water properties and main particulars of both model and ship. Sixth, the form factor was determined using the Prohaska method by selecting results corresponding to float numbers below 0.2 and CTM over CFM versus FN to the power of 4 over CFM was plotted. 7. The total resistance of the model was extrapolated to the full-scale ship using ITTC 1978 performance prediction method for the given ship particulars. Finally, the effective power versus ship speed in knots was obtained.
Next, we will be moving to result part. First is plot pro ASCA. The main finding of this graph is used to find the hull's form factor 1 plus k, which is determined by the y-intercept 1.2384. The threadline equation is given as y is equals to negative 1.8077x plus 1.2384. Second is CTS versus RNS graph. So the main finding of this graph is the total resistance coefficient CTS decreased steadily from 6.310 10 power of negative 3 10 power of 3 to 2.9 times 10 power of 3, as the speed RNS increases. So the reason is this downward trend is expected because viscous resistance coefficient decrease as the Reynolds number increase, dominating the total coefficient profile at this lower to mid speed range before wave making completely takes over. As for CFS versus RNS graph, the main finding is the frictional resistance coefficient CFS decreases smoothly from 4.42 times 10 power of negative 3 to 3.79 times 10 power of negative 3. So the reason is as the velocity increases, the turbulent boundary layer thins relatively, causing the non-dimensional frictional drag coefficient to decline. So next is CRS versus RNS graph. So the main finding is as the ship's speed and Reynolds number RNS increases, the residual resistance coefficient CRS drops sharply from a positive value of 0.5 times 10 power of negative 3 straight into negative value, reaching as low as negative 2.2 times 10 power of negative 3. So the reason is the form factor 1 plus k used in the exponential mass was overestimated, subtracting too much viscous resistance and forcing the wave resistance below zero. As for RTS versus FNS graph, the main finding is the total ship resistance force RTS display an abnormal U shape curve dropping from 8.75 down to a minimum near 8.0 at FNS is equals to 0.175 before climbing up towards 8.5. So the behavior of this graph shows the total force should strictly increases with the speed. The drop confirmed that the fall pro-ASCA calculation corrected the low speed result. Next is PE versus FS. So the main finding of this graph is effective power PE increases exponentially from 36 kV to 74 kV as the speed of ship VS goes from 4 to 9 knots. So the result highlights that as a ship goes faster, the power required to overcome the water resistance scales aggressively.
Assalamualaikum, my name is Siti Nur Alisha. Now, I would like to discuss the result obtained from the resistance prediction analysis. First, based on the ITTC 1978 method, ship resistance is expected to increase as the ship speed increases. This is because at higher speed, wave-making resistance becomes more significant and contributes more to the total resistance. However, in our result, the resistance values remain almost constant at different speed. This is not what we normally expect, and it suggests that there may be some issues with the model test data. Next, when I compare the extrapolated result with the MaxSurf prediction, I found a very large difference. MaxSurf estimated that the vessel would require around 10,000 to 15,000 kilowatt of power at 70 knots, whereas the model predicted only 74.227 kilowatt. This clearly shows that the model test significantly underestimated the actual power requirement of the ship. There are several factors that may have caused this discrepancy. The factor affecting model shape, including laminar flow, effect on the small scale model, limitation in load cell sensitivity during measurement, and tank blockage effect that can influence water flow around the model. So based on this finding, the recommended propulsion system is a marine diesel engine with a fixed pitch propeller and a semi-balanced rudder is recommended to ensure efficient and reliable ship operation. Overall, although the ITTC procedure was applied correctly, the experimental data contained uncertainties, making the MaxSurf prediction more realistic for full-scale ship performance. That's it.
Assalamualaikum. My name is Nur Shazwani Binti Ismail. My meter number is 72140. So, in conclusion is the ITTC 1978 conclusion were complete successfully, but the model data was unreliable because the resistance remained a most constant instead of increasing with speed. This caused an unrealistic for scalar power prediction of only 74.27 kilowatt compared to the expected 10,000 until 50,000 kilowatt. Therefore, the final result design should use corrected empirical data to select a marine diesel engine and fit piston propeller (SPP) and conventional speed or semi-balanced rudder. That's all.